As long as you have one-to-one mapping, this function is called inversible. Okay, meaning you can invert. You have one value of x, you have corresponding value of y, you change your position. Now for every value of y, you have corresponding one value of x. Now come back to this point. The same thing that I was trying to do, which I deleted on purpose. What happens here? Now, from this side, for every value of x, you have one value of y. Now you change your position. You came here. And for minus, when you look at this inverse function, minus 7 relates to 0. Okay, this is fine. Minus 11 relates to minus 2. Wonderful. 1 relates to 4. So far so good, no worries. But this guy is getting me confused. For minus 3, I have two possible answers, 2 and 6 for the inverse function. And you will never ever have a function which will give you more than one result. Meaning, if your y is a function of x, which equals, let's say, x square minus 6, x square minus 6 will give you only one value for every value of x. If you get x equals to 4, you can get only 16 minus 6, 10. You cannot get 10 and something else. For x equals to 4, you can get only one value of y, which is 10. You cannot get any other value. Meaning, when you change the domain and range, when you flip it, when you make it inverse, the behavior should not change. Meaning, for every input, there has to be only one output. Here in this case, for two of the inputs, there is one output. And when you go to this side, you look at this, for every input, there is only one output except for number minus 3, which is giving two possible outputs, and that gets you confused. All of us confused. And then we say, okay, now we cannot inverse this. This is a non-inversible function. Meaning, as long as you have one-to-one mapping between the input and output, this function will be inversible. If whenever you see one to many or many to one, that cannot be called as a function which is inversible. Is everybody with me?
So I have a question.
Yes,
so the inverse function can have two outputs for each input?
No, it cannot. See.
Oh, sorry, I meant two inputs for each output, or like.
No, so whenever you have anything which is more than one to one, okay, be it one to many or many to one. So let's look at some examples, okay. Let's say you have two functions, okay. I'm not putting the function formula. I'm saying that you have two functions. 1, 4, 3, minus 2, minus 6, 4. Okay. Versus this one. 2, 6, 8, minus 1, minus 6. That's it. Here, you look at this team or this team. Both have only one opponent. Okay. I'm giving some relatable examples, okay. So every input, this is my input, this is my output, this is my domain, this is my range. Whichever way you want to remember this. For every input, I have one output. When I change my side, if I look at this input, there is only one output. This is inversible. Come to this. From here you should see. So if this is relating to function of x, y equals to function of x, which is something, let's say 4x minus 2, whatever. I'll forget about this because I'll get you confused. So if this is a function, this is inversible. We will say that, okay, this is inversible, meaning there is a possible inversible function for this scenario. If you look at this, if this is something called y1 equals to function of x1, okay, here in this case the inverse function is not possible, because as long as you are on this side, every input has one output, every input has one output, every input has one output. You come to this side, every input doesn't have one output only. There are few inputs which is resulting into multiple outputs. This is not inversible. You cannot, you can, here you can have inversible function. This is an inversible function because input to output, output to input, that flipping you can do. Here you cannot. Yeah?
Yeah, I got it.
Now,
Yes.
so basically, in simple terms, wherever you see multiple lines meeting one point, be it on any side, okay, be it on this side or be it on this side, both are non-inversible function, because whenever you have multiple one to many or many to one relationship between the domain and range, that will not qualify for being an inversible function. Yeah.
Yes.
Now let me try getting you guys a little bit more confused. Let's see if I can do so successfully. So see, it is a rivalry going on between me and you guys. Okay, I'm trying all possible ways to get you guys confused, and you guys are trying to defend that. Okay, it's like I'm firing weapons and you guys are kind of holding it. Now let's say if I have function y as a function of x, which equals x squared. Okay, if I asked you whether this function is inversible or not, what would be your first response? Or how would you think about it? See, your teacher is firing at you now.
It is inversible.
Say that again.
It is inversible.
Okay. Think about it. Okay. I love reasoning. Okay. So I mean, not for you guys, but when I'm teaching, younger kids, I say I don't care about the answer, and that I mean it. I don't really care about the answer. What I care about is the approach, how you are going about it. Yes, Dave, tell me.
I don't think this function is inversible because this is a parabola, meaning at a y value, there's like like two x's have the same y value. So when you flip it, the y would have two x values. So it can't be inverse.
Yes. You are spot on, Dave. Okay. I'm not saying that Ishwari was wrong. Ishwari made a good attempt, but my weapon was stronger than your defense. Let's look at it. So what Dave said here was this. Now I will probably not think about it too much. Okay. Like Dave probably thought too much about it. He said, oh, this is a parabola, and parabola, there could be two possible values. I will not even go there. What I will do is, I will do it like a child. Let's plot a table of x and y. When x equals 0, y is 0, no problem. When x is 1, y is 1, no problem. When x is 2, y is 4, no problem. I wanted to do something mischievous. How about minus 1? Gives me 1. This is what they told. If I do minus 2, what do I get? 4. Now, here is the convention. Yeah? Are you able to relate to what I'm saying? Meaning, if this was your domain, I mean, if this is your domain and this is your range, what do you see? Yeah? This is not inversible. Yes. Now, since we all know about parabola, we know that it's a parabola, so there will be two possible values which will possible values of x which would come to the same y. That's how it becomes many to one, and it's not inversible. Yeah. This is one way of looking at it. Is everybody with me so far?
Yes.
Am I successful in confusing you guys so far? Am I successful in confusing you guys so far? Tell me. Nobody is saying anything. My question was, am I successful in confusing you guys? What would be the right response? Yes or no?
No.
No.
Or yes. I'm not sure.
Sorry, say that again. Sally?
I'm not really sure if you confused us or not.
So yeah, I mean, see, this is part of my teaching, right? Where I say try. See, the question could be as stupid as you can imagine. I said, am I successful in confusing you guys? That was the question. I'm not saying that will be a silly question, but what it comes down to is reading of the question. Okay? Just read. Read the question again and again. I said, am I successful in confusing you guys? When you read that, then A stands for analysis. Say, okay, no, he's saying, am I confusing you guys? Am I confused? No, I think I'm not. Then comes your Nike. Just do it. Then you'll say no. If I'm successful in confusing you, then you'll say yes. You have an opportunity to teach it one more time. Yeah. Alright. So that is the lighter side of math. Let's come back to same function y equals to fx, which is x squared. Okay, so this is the relationship between y and x as per this function.
I have a question.
Yep, yeah, Chris.
Why do you write y equals fx equals x squared and not just directly fx equals x squared?
I can do that. That is as per the definition. But I'm saying that this function yields into something which I will plot on my y-axis. That's why I'm saying that, okay, we are more familiar with x and y, right? And we will probably use that for drawing it on a coordinate plane. So that's why wherever you have a function of x, you can assume that, okay, it's another variable, and that comes as an outcome of this one. So basically, when you have a function like this, you have a domain and a range. If you're saying your domain is x, you get tempted to say your range is y. That is why I'm putting a y.
Oh, that makes sense. Thank you.
Now, so see, I'm a very, what do you call it? I'm a very nagging person. I keep nagging each one of you, and there's a reason to it. Like when I asked you guys to explain me the approach, right? Ishwari and Dave both gave their definition, and both are good at it. Dave said that it's a parabola. Yep. So whatever we have put in the table, that's what it draws. It's a parabola. Yep. So Dave, I cannot disagree with what you said, but I'm not putting all that effort just for saying yes, Dave. I have an intention behind. So if you have a function like this, which draws something on a coordinate plane as x and y, you can do a horizontal line test. See, you put a horizontal line. If it cuts the parabola or whatever curve you have at two places, this is a non-inversible function. See, you have multiple options. This is called horizontal line test. You can literally draw a horizontal line which can pass through this. And when you look at this horizontal line, what does it mean actually? This horizontal line is on the y-axis, right? This line says y equals to, let's say this is 1, 2, 3, 4. Okay? 1, 2, 2, 3, 4. Okay? Means for one value of y, when y is 2, there are two possible values of x. Yeah, you see that? These two? So that is what this horizontal line test means. This is again repainting the same thing in a different way. Meaning there is one value of y, you have two possible values of x. Either another value of y, let's say this is y equals to 4. This line is y equals to 4. This is y equals 2. For value of y equals 4, this line is crossing this curve or the parabola at two places. So for every value of y you have, for multiple values of y, you have two values of x. Yeah. So when the line cuts the curve at two places, the horizontal line cuts at two places, that means you failed the horizontal line test with respect to this function. Meaning whenever this fails the horizontal line test, that is when you will say that this is non-inversible. Yes, Dave.
I just have a clarification question.
Mhm.
Do horizontal lines always tell you the inverse function if it's an inverse function? And do vertical lines always tell you if it's a function?
Vertical lines, yeah, that is correct. Yeah, I mean basically horizontal line tells you that if the horizontal line cuts the curve at two places, that means for every value, for that given value of y, you have two possible values of x. So this cannot be inversible. It is non-inversible. Okay.
Okay, thank you.
So now look at another situation. If I'm looking at this thing, if we talk about the same horizontal line test, let's say you have a function something 4x cube plus 2x minus 7, something like that. Okay, and then you make a table of x and y, and then you join the points and plot it. Now if you look at this guy, it will not fail the horizontal line test. This is inversible. Are you guys with me so far?
Yes.
Yeah, Dave.
Yeah, I just have one more question. So, if you're like giving questions like this on like the SAT, for example, so would a quick way to answer this, would it be like any function with a odd degree? Is that always going to be inverse function?
You are a little ahead of me. So yeah, I was coming to that. Okay, that was the next thing. Okay, so far I was just trying to make sure that whatever I have told, that is digested and processed before I go on to the next concept. Yeah. So everybody understood this horizontal line test, plotting graph from a function and figuring out which one is inversible versus which one is not. Correct? And unfortunately, you all are forced to say yes or no. If you don't say so, I would not know. If I need to proceed further, I need to stop.
It was clear.
Okay, everybody? Okay. Yeah. Well, then some of you keep giving feedback in between. That keeps me awake. Okay. Otherwise, I might fall asleep standing. All right. So simple thing is this: when you have any curve based on the function and it doesn't fail the horizontal line test, this is inversible. Now think about a scenario where your curve is like this. Do you think this is going to be inversible or non-inversible? Just give me a response based on optics. Do you think this is inversible or non-inversible?
Non-inversible.
Yes. Why so?
Because it doesn't pass the horizontal line test.
Yes. Because there are places there are places like this from basically in this range, at least from here to here, you can draw so many horizontal lines which will make this fail the test, and that is why it is non-invertible. Correct? So anything which is a quadratic equation, y equals function of x, which is equals to 4x squared minus 2x plus 8, let's say. It will be a kind of a parabola. It will lead to a parabola only, because every quadratic equation draws a parabola. Doesn't matter whether the parabola is like this or like this or like this or like this or like this, or maybe here or maybe here, maybe here. It will still be a parabola which will have an upward curve and a downward curve, or a downward curve and then upward curve, whichever way it is. But there's something about the parabola that we all know, that it has a quadratic equation to it, meaning the maximum power to the variable is 2, that you see here. And as soon as you see a power of 2, like we saw in the previous example, y equal to x squared, it did not ring the bell for saying this is a parabola immediately. I mean, we as a normal human being, we are tempted to see it like more like an equation, just having one term doesn't remind us of this being an equation for parabola, unless you are super cautious like what Dave did. But then if I were Dave, I would have probably thought, okay, is this a parabola? Maybe, may not be. I mean, unless I would have thought enough, I would have probably not assumed this to be a parabola, but this is actually a parabola. Any quadratic equation, meaning any equation where the maximum power to the x or the variable is 2, leads to a parabola. And when you have a power of 2 or a square, that results into a symmetric structure when you try plotting it on a coordinate plane. And if it's a symmetric structure, meaning it goes up and comes down, or vice versa, comes down and goes up, it will always fail the horizontal line test. So I certainly don't want you guys to memorize this, but a quick tip is, if you are dealing with a quadratic equation, that would be non-invertible always, because a quadratic equation leads to a parabola. Parabola never passes the horizontal line test, or parabola will never ever pass a horizontal line test. Make sense? Yes, it's very.
I did that by accident.
Okay, no, I took that as a yes. Okay. Are you guys with me so far?
Yes, sir.
There.
Now, there's one more dimension to what we have seen so far, and that will be probably the last concept for today. I think we are already talking the hour. Now, if let's say you have any equation, any function, okay? I'm always writing this as y equal to function of x. The reason being, we always keep that in mind that, okay, my x is resulting into an output. My domain is giving me a range. Okay, that's why I write it like this, but you can choose if you want to write it that way or not. Why 4 always? If I have an equation like this, and let's say this results into this, I'm just making it up. You can always say, and you could be asked questions like, okay, for what segment or piece of this curve it will be inversible. So you can say, okay, from here to here, if you look at only this piece of the curve, or only look at, let's say, okay, here to here, this will pass the horizontal line test. So there could be questions. They will say, okay, fine, which part of the curve is inversible. And then you have to look at the possible value of x and y. This is your y, which is nothing but the output or the range, and the other inputs. So you can always say for value of x equals whatever is here and here, okay, this is inversible or vice versa. Okay, I mean value of x or value of y, this is inversible or non-inversible. So there will be questions. So basically, what I would want you guys to do is now related to this. Yes, Chris.
I just had a question. So you said like for a parabola, so a parabola would never pass the horizontal line test. But then should we take a note that for a cubic function, the cubic function will pass the horizontal line test sometimes?
Cubic. So basically, yeah. I mean, that's a good call out. So basically, mostly what happens is, I mean, you guys can try this, but if you have a cubic function, that always yields into a graph like this. Okay, so you'll see that if the function has power or an odd power, okay, meaning 3 or 5 or 7 or 9 or -3, whatever, right? If the maximum power to the variable is an odd number, then that will be inversible, because then you will not have the same loop of matching value of x. I mean, you can simply look at this y equal to x cube. For no scenario of x, for no possible value of x, you will have the same value of y. If it's 1, it's 1. If it's -1, it's -1. If it's 2, it's 8. It's -2, it's -8. So if the power is an odd power, it is almost 100% sure that it will be inversible. If the power is even or it's like a quadratic equation, it will be non-inversible. I mean, that could be an interpretation from what we have seen so far. You still might want to get your hands dirty by picking up some quick example, so some questions or equations, and try putting that in a graph and see whatever we are discussing here is something that gets proven or not. I mean, conceptually, yes, any cubic function will be inversible, any quadratic function will be non-inversible. That's the concept part of it. No harm in trying 1 or 2 problems and just to ascertain that this theorem cannot be proven wrong. Yeah.
Oh, okay, sir. Thank you.
Yep. So that is where I would want